in this comparison. So that was the story of the producers. They produced food from the carbon dioxide and water with the help of drawing energy from the solar radiation, and that utilize part of their food for their own purpose. How much? 50 to 70% was utilized for their own purpose, and the rest was utilized for their growth, that is the production of the biomass, and that biomass is made available to the next trophic level. So these producers are then consumed upon by the consumers. So in our basic lecture, basic segment, we have seen that the energy flows from producers towards the consumers. So the consumers, that is the primary consumers, are herbivores. So these consumers consume upon the biomass of the producers, and these consumers at this level, at the level of primary consumers itself, they can be divided into two groups. One group is herbivores, which feed upon the live plant biomass, which feed upon the plant biomass, whereas the detritus feeders, that is the plant biomass which is converted into dead organic matter after death of the plants, they are also acted upon by the consumers, and those consumers are detritus feeders. So the consumers beginning with plants are producers, and consumers come into picture after the plants. So the consumers which feed upon the plants or consume plants, they can be broadly categorized into two categories. The first category is the grazers or the herbivores, which feed upon the plant directly, whereas the total plant biomass is not fed upon by the herbivores themselves, but a major part of it is reduced into detritus after it deaths, and that is acted upon by the detritus feeders, which consume the dead organic remains of the plant and carry out mineralization. So the production by plants, consumption begins with two lines. Herbivores, which are grazers, eat upon the plants. They consume part of the plant biomass, whereas the major part is consumed by the detritus feeders. Now, when we assess about the extent which is fed upon by the herbivores or which is subjected to the detritus food chain, we come across that plants are well fortified. That is, the plants have got so many adaptations on their surface. Chemical adaptation, they produce certain chemicals which are very pungent and which are not liked by the grazers, and so they are not grazed upon. They produce certain chemicals which are not digested upon well by the grazers, so they are not grazed upon. So plants in course of their evolution have developed many adaptations, many protections which protect themselves from the grazers. Although a major portion of the plant is grazed upon, but when we take into the total biomass produced by the plant, only 10% of the total biomass is consumed by the grazers, whereas 80 to 90% of the dead biomass is consumed by the detritus feeder. So, although apparently in our vision, when we look upon, it appears that the plants are being grazed upon by the grazers. No, only 10% of the plants, that is the total, out of total biomass of the plants available, only 10% are fed upon by the, only 10% of the biomass is consumed by the herbivores, and it has been deduced, it has been assumed, it has been seen that this is due to the protection developed by plants in course of evolution against the herbivores. So when 10 to 20% are grazed upon by the herbivores, the rest 80 to 90% of the dead plant biomass is consumed by detritus feeder. So we should have a clear idea that we should not get confused, because it is the grazers which meet our eyes and we see them grazing upon the plants. So we come to the conclusion that it is grazers that are the major consumers of the plant parts. But we should know, we should stress, we should underline that only about 10 to 20% of the total plant biomass produced as net primary production is utilized by the grazers, whereas 80 to 90% of the dead plant biomass is consumed by the detritus feeders. These consumers, whether they are herbivores or detritus feeders, again utilize the major parts. Yes, what happens that when this transference occurs, when from the primary producers to primary consumers, when the biomass is transferred, when energy is transferred, total energy is again not made available for the next trophic level. Rather, a major chunk of the energy is utilized by the consumers themselves for running their vital activities, and only the remaining part is made available to the next trophic level. So it is not that the total that the consumer gets is transferred, but only a part of it is transferred and a part is utilized for biomass production, which is available to the next trophic level. The amount of new biomass produced by consumer is called secondary production. So primary production was by autotrophs. Production by autotrophs utilizing the solar energy through the process of photosynthesis. But when this transfer takes place, when consumers consume upon the plants, they again utilize part of their consumption for their own activities and make available the rest for the next trophic level, and the amount of new biomass that has been produced by consumer is called the secondary production. Now we should have an idea of the efficiency of the production. That is, how efficient is the system, how efficiently the production takes place. We have seen how efficiently the primary production was taking place. That is, out of the total impulse energy, how much is being utilized for the production of their food by the plants, and that was the efficiency of the primary production. Now let us see the efficiency of productions, that is, consumers are how much efficient to produce their foods. So the production efficiency here defines how well an organism uses the energy that has been assimilated by it as food. Okay, so by efficiency of production, we try to assess that how much of energy the animal has assimilated and what proportion of that energy is utilized for the production. So out of total energy gained, how much it can utilize for production, that is the production efficiency. It is net production by assimilation into 100. When we have a look upon the production by the vertebrates, invertebrates, and different groups among the vertebrates, we come across a strange data. So the production efficiency of vertebrates, although vertebrates stand taller because they remain on the higher level of evolutionary ladder and they are more visible they look more efficient, they are more evolved, you can say. But the efficiency of production is less in them. Why? The vertebrates, though they are more evolved, they are more efficient in carrying out their life activities, but they are lower on the ladder of production efficiency because the life activity of vertebrate involves consumption of lots and lots of energy, and so the respiratory loss is maximized in case of the vertebrates, and that's why the energy utilized for the biomass production in vertebrates is far less than in invertebrates because the respiratory loss in vertebrates exceeds far more than that of invertebrates, and that's why the vertebrate, that production efficiency in vertebrate is lower than invertebrates. Among the vertebrates, you know, two groups exist, endotherms and ectotherms. Endotherms maintain constant body temperature, and ectotherms change their body temperature according to their surrounding, and they have certain spatial adaptations through which they maintain their body changes in a range which is fit for their survival, and they have major adaptations, rather behavioral adaptations, and they have estivation, summer sleep and winter sleep, etc. So they don't have to spend too much energy on maintaining their higher body temperature or a constant body temperature. On the other hand, the endotherms, they maintain constant body temperature throughout their lives. And this maintenance of constant body temperature has given them an edge over the ectoderms in many ways. It is beneficial in many ways, but in some ways, that is, as far as the efficiency of production is concerned, what they produce, a major chunk of that part is utilized for respiratory activities because they need more energy for maintaining constant body temperature than ectoderms. And that's why the efficiency of production is far less in endotherms, because for maintenance of constant body temperature, endotherms require 98%, too much. It's 98% of assimilated energy which is utilized for carrying out life processes, particularly for maintaining the constant temperature throughout the life. And so 98%, 98, mind you, 98% of the assimilated energy is required by the endotherms for maintenance of their body temperature and activities, and in ectotherms it is only about 9%. So vertebrates have got lower efficiency than invertebrates. Invertebrates, endotherms have got far lower efficiency than ectotherms, and this is because endotherms utilize 98% of the energy for carrying out their life activities, whereas the ectotherms utilize only 90% and 10% is available for the next trophic level. Thus, production efficiency of about 10% is common for ectotherms, whereas in endotherms it is 1 to 2%. Very meager amount, 1 to 2%. Out of total production, only 1 to 2% is available for the next trophic level, and they consume 98% of what they produce. So the production efficiency is also higher in young animals also. So the production efficiency varies in vertebrates and invertebrates, and invertebrates, different groups of vertebrates too. Now, efficiency of consumption. This is called consumption efficiency. That was efficiency of production by the heterotrophs, and here the efficiency of consumption. How the consumed part efficiently used. So consumption efficiency measures the amount of one trophic level eaten by the other trophic level above that is incorporated into the latter biomass. So the amount of one trophic level. Consumption efficiency measures the amount of one trophic level eaten by the trophic level above that. So if you consume, and say for example, we are talking about the herbivores, about the grazers. So grazers are consuming upon the plant parts. So how much of the plant parts that has been consumed by the grazer is available for the next trophic level, and that biomass gives us the consumption efficiency. Consumption efficiency can be obtained by dividing intact at a trophic level N, the consumption efficiency can be obtained by dividing intake at trophic level N by net production of trophic level N minus 1 into 100. So if we are talking about the grazers and plants, how will we derive or obtain the consumption efficiency? We will see that how much the herbivores are taking in from the plants, and how much was available at the plant level. That means trophic level N here is the plant, and trophic level N here is the herbivores, and trophic level N minus 1 is plant. So if the available energy at trophic level N minus 1 is divided by, if intake at trophic level N is divided by the energy available at the preceding trophic level, that is N minus 1, and if the data obtained is multiplied by the 100, we can get consumption efficiency. Let's have a look at the consumption efficiency once more. Here I have used two terms, trophic level N minus 1 and trophic level N. Trophic level N is a certain trophic level. N minus 1 is the level just preceding it. That is, if the trophic level N is herbivores, N minus 1 is the autotrophs. So if we divide the trophic energy intake at trophic level 1 by N by, if we divide the intake at trophic level N, that means in this example the trophic level herbivores, that is divided by the net production at the trophic level autotrophs, and then it is multiplied by the 100, it will give consumption efficiency. Consumption efficiency generally ranges between 0 to 15% for terrestrial herbivores, meaning thereby that 85 to 100% of net terrestrial plant production goes into the decomposition chain. So this is the point which I have stressed earlier too, that when the herbivores eat upon the plants, it is not that the total energy of the plants, the net primary production of the plants goes to the herbivores. No, apparently at the level of look, it appears that the grazers are grazing upon the plants and they are getting the entire plants. But in reality, it doesn't happen. What happens? That 0 to 15%, only 0 to 15% terrestrial herbivores, a consumption efficiency in terrestrial herbivores ranges between 0 to 15%. That is, only 0 to 15% is available for the terrestrial herbivores, and the rest goes to the decomposer chain. That is the detritus food chain that I have stressed earlier too, that the plants have got certain protective adaptations which prevent the herbivores from grazing it or denuding it, grazing it altogether or denuding it. And so only a part that is 0 to 15% is utilized by the herbivores, and the rest is given to the detritus food chain upon death and decay of the plants. The carnivores, however, consumption efficiencies may reach 50 to 100%, showing that animals are much more better equipped to digest meat than to detoxify and digest chemically protected plants. This point stresses upon another fact that, as I have told you, that plants have been protected, have been fortified so that they could not be consumed by the grazers. But the animals utilize 50 to 100%. This efficiency in animals, it goes up to 50 to 100% because the animals themselves have not been that protected against those animals which are feeding upon them. So that in case of primary carnivore to secondary carnivore, it is 50 to 100%, but in case of primary producer to herbivore, it is only 0 to 15%. So herbivores get far less of the plants, and major chunk of the plant biomass goes to the detritus food chain upon death and decay. But once what the herbivores get, its major chunk is transferred to the carnivores and to the higher level of carnivores onwards. Then there is a trophic level transfer efficiency. Trophic level transfer efficiency is measure of the energy available at one trophic level that is acquired by the trophic level. So this efficiency, trophic level transfer efficiency, it measures how efficient is the transfer of energy from one trophic level to another trophic level. So how much energy is available is at trophic level X. How much energy that is available at trophic level X is passed to trophic level X plus 1, and that is the trophic level transfer efficiency. We can obtain trophic level transfer efficiency by dividing assimilation at trophic level N by assimilation at trophic level N minus 1 into 100. Here also the trophic level N represents a trophic level in question, and N minus 1 represents trophic level just preceding that we are considering. For example, if we are considering the secondary carnivores, the efficiency assimilation at trophic level N is assimilation by the secondary carnivores, whereas assimilation at trophic level N minus 1, that is assimilation by the primary carnivores. So N minus 1 represents the just preceding level which is being considered. If we are considering trophic level 1 or trophic level N, for example, if the trophic level N is the secondary carnivore, the N minus 1 is that primary carnivore. So if energy assimilated by the secondary carnivore is divided by the energy assimilated by primary carnivore, and then it is multiplied into the 100, we get trophic level transfer efficiency. So let us have a look how this trophic level transfer efficiency varies. Trophic level transfer efficiency appears to average around 10%. So trophic level transfer efficiency, when we discuss that trophic level, how efficiently the energy from one trophic level is being transferred to the another trophic level in the consumers, we come across the data of 10%. 10% is meager. Out of 100, only 10%. So efficiency is very, very, very poor, you can say. What are the causes of this poor efficiency? The first is that out of what has been eaten, only a part is digested and a major chunk remains undigested. So only the portion of the biomass which had been efficiently or effectively digested is made available to the animal, and the rest is undigested portion is excreted out. So here see that many organisms can't digest all parts of their prey. They can't digest the hard bones. Only a few organisms such as hyenas can digest total animal parts, even hard parts. So a major chunk which an animal feeds upon another animal is passed out as undigested remain, and so that digested portion could not be utilized as energy for production of the biomass. That's why there is this energy is only 10% efficient in this trophic level transfer efficiency is only 10%. Secondly, much of the energy assimilated by animal is used in maintenance. As we have seen that the higher organisms, the higher level carnivores, they utilize much of the energy for their own maintenance, for respiration. We have seen in the case of endotherms that how much of the energy is utilized for maintenance of constant internal environment, constant internal temperature, body temperature throughout the life, and so they burn out, they oxidize a major portion what they have eaten. So there are two reasons for low efficiency. Reason one is total part that has been ingested is not digested. A major chunk of the animals such as bones, nails, etc., they are having those portions, have got energy, they could have produced biomass, but they could not be digested by the animal concerned, the animal which is feeding upon them. So these portions are passed out and they could not contribute to the biomass formation. Second reason is that these animals spend much of what they have got in the form of the biomass transfer from their preceding trophic level. They spend much of what they are getting into their maintenance, into carrying out their life processes. So their life, their physiology, their lifestyle is such that they are energy centric, you can say. They utilize bulk of the energy that they get from the previous trophic level, and that's why the trophic level transfer efficiency is very low. The 10% transfer energy of energy from one trophic level to another trophic level necessitates short food chain. Now, here is very important point that you should stress upon is that longer, if the trophic level transfer efficiency is not that good, that is, it is near about 10%. So from one trophic level to another trophic level, energy available from one trophic level to another trophic level will diminish considerably while the transfer is taking place. So if you have got a long food chain, that is, there are too many connections, there are too many trophic levels, and efficiency going down at such a big rate, what will happen? The energy will dissipate, reaching second, third, or fourth connection of the food chain. That is, while the energy is transferred from autotrophs to heterotrophs, only 2 or 3 levels of the heterotrophs will get sufficient energy for their survival, and then the flow of energy, the availability of energy will diminish considerably, so that it would not be sufficient for enabling the animal to carry its life activities. So that is why 10% transfer of energy from one trophic level to another trophic level necessitates short food chains. Longer the food chains, lesser will be the amount of energy available to those trophic levels which are linked at the end of the food chain. So they will face deficit of energy. If the food chain is shorter, if there are a few trophic levels, even the even though the efficiency is low, they can be served. But if the chain goes undue longer, the last attachments, the last trophic levels which are attached to the chain, they won't get appropriate energy, and it would be difficult for them to sustain life activities. So most with no more than 4 or 5 links, as little energy is left then to be passed over to the higher levels. So taking into the account this low efficiency of trophic level transfer, we cannot add so many trophic levels in a food chain, because the energy diminishes considerably after 4 or 5 attachment, that is after 4 or 5 trophic levels. And so the 5th, 6th or 7th won't get proper energy, substantial amount of energy for carrying out their life activity, and so it will be difficult for them to sustain their life on this food chain, on this base of the primary producers. So while discussing the fixation, transfer, dissipation of the energy through the ecosystem, we have come to the conclusion that the primary producers are the plants, mainly plants, because it is the plants which have got the ability to fix the solar energy, and they can get energy from the sun and utilize those energy for synthesis of their food during the photosynthesis, in which carbon dioxide and water is utilized, getting energy from the sun to synthesize into the carbohydrates. And this energy synthesized by the plant is not totally available to the next trophic level, because part of this energy is utilized by the plants for sustaining their own life activities, and only the rest, that is the net primary production. Total production is the gross primary production, and gross primary production minus respiration is the net primary production. So only the net primary production is available. Now this total net primary production, that is the point to be underlined. I have discussed in the second or third slides and in the penultimate slide also, that it is not that the bulk of the gross primary production is available to the grazers. Only a very small portion of the primary production is available to grazers, because plants are well fortified and they have developed, in course of evolution, developed certain adaptations which dissuade herbivores from eating upon the plants. So a major chunk of the plant body, of the plant biomass, is acted upon by the detritus food chain upon the death and decay of the plant material, whereas a very small portion of the plant biomass is ate upon by the herbivores live in course of the transfers of energy that meets our eyes. Now this production is again transferred, production by the consumers is again transferred to the secondary consumers, tertiary consumers, and the efficiency goes lower and lower. The trophic level transfer efficiency, as we have seen here, is only 10%, and so at this efficiency, at only 10% of the efficiency of transfer, we cannot go too long down the food chain, and the number of the trophic levels that should be attached to an engine of the primary producer should be very less. About 2, 3 or 4 stages can only be served, because the efficiency is very low, and the energy acquired through the transfer, energy fixed by the plants, the primary producers, is passed upon to the consumers in such a way that a lot of energy dissipates according to the laws of thermodynamics, and so that's why the number of trophic levels supported by a primary producer level should be very low. Otherwise, the last trophic levels won't get substantive amount of energy for sustaining their life process. So we have got an idea of laws of thermodynamics, of primary production, net primary production. We have got an idea of the gross primary production, and we have also idea of different types of production, consumption, and trophic level transfer efficiencies. And that shows that how energy is passed from one trophic level to the another trophic level, and how much energy is available to the next trophic level from the preceding trophic level. So that's how we have got an idea of energy transfer in the ecosystem. But we have again to draw different models of energy transfer. We can based upon these data, we can draw a model which can be visualized, which can be reflective of what we have seen in course of these slides. So on the basis of the knowledge gained through these slides and data obtained through these efficiencies and the production levels, we can draw different models of energy transfer. These models can be self-explanatory, and they can themselves explain that how energy is being transferred from one trophic level to the another trophic level, how much energy is being lost. In case of transfer, how much of energy is being consumed by a particular trophic level, how much of the energy is lost during the transfer from one trophic level to the another trophic level, and how many trophic levels can be attached to one engine of primary producing trophic levels. So that modeling we will see in the next class. Thank you for joining me, and I hope you must have got the idea, and I must have reached all of you through my explanatory notes, through my explanations. I have tried my level best, but if you have some confusions, you have certain misgivings, you are free to raise these questions telephonically or during the live interactions or through the messages. So thank you all for joining me, and it was a pleasure for me to be among you and discuss these nuances, these intricacies of the energy transfer to different trophic levels of an ecosystem. Thank you. Thank you very much.